Good morning, everyone, and welcome to section 4.3. In this section, we look at the concept of a discrete random variable. So you can see I've already written that a variable x is a random variable if the value it assumes in the outcome of an experiment is a chance or random event. So some examples of random events, for example, the result of a coin flip. The idea here is you're performing an experiment and you do not know what the outcome is going to be. The outcomes do not have to all be equally likely. So here, for example, the coin does not have to be fair. That's a chance event. You could roll the sum. You could roll 2 dice, and the sum of 2 dice when rolled a random event could be the first card dealt in a card game. So these are all random events. Oh, should write first card here. First card dealt in a card game. These are all random events, and I'd like you to notice in particular the middle one, that when you are asked what the outcome is, that you will give a number, and then that number will be a discrete random variable. And we can call that our variable x. So a discrete random variable then is quantitative. It has a numerical value in the way that the sum of our 2 dice is a numerical value, and the discrete part means that, well, we looked at discrete variables earlier, but I'll remind you that that means it can only take on certain values. And for example, 2 6-sided dice can have a sum of 3 or 4, but not 3.75 or pi or something like that. And so they come in steps, essentially. So we should now look at the idea of a probability distribution. Handwriting's crappy today. Probability distribution. And it really sounds a lot more complicated than it is. So, example, when you roll a fair 6-sided die, remember 1 die, 2 dice, what is the probability of each roll? And you could simply say, give it that in a sentence. You could say, oh, well, there's 6 possibilities. They're all each equally likely because of the word fair here, and that means they're equal to 1/6. But you could also, if you wanted, this seems like a little bit of overkill here, but you could write it as a table. You could say the roll you can get 1, 2, 3, 4, 5, or 6, and then the probability of each roll is equal to 1/6. It's a bit repetitive, but bear with me on this. There's a reason for going along here. And if you notice, the sum of all these is equal to 1. If you had them in percentages, then the sum would be equal to 100%. You could also show a graph. Again, it's not going to be a very entertaining graph, but if, for example, you had 1, 2, 3, 4, 5, 6, and our axis is the roll, and our y-axis, so that was the x-axis, or y-axis is probability. I could call that capital P if I wanted, I suppose. And then this is the value 1/6. And it's our uniform distribution that we talked about earlier, so there's really not a lot of features on this graph. But those are the two ways of representing our answer, which is the probability distribution for this particular experiment, which is rolling one fair six-sided die. So I'm going to say it verbally and then write it down later. The probability distribution for a discrete random variable is a formula, graph, or table that gives the possible outcomes of x and their associated probabilities p of x. So let's do another example, which is a little less uniform, which is what is the probability of each outcome for rolling an unfair six-sided die if the probability of rolling 2, 3, 4, or 5 is still 1/6, but the probability of rolling 1 is 0. There's a defect in the die, maybe it's rounded and it won't even balance on the 1 or something like that. Then you could still do a table. You could also do a graph, leave a little space on the right, and our roll. And here we can either write roll or x, and then the probability of the roll. Should use a lowercase p here. Then we've got the probability of 1 is 0, and then 1/6, 1/6, 1/6, and 1/6. We know that the sum still has to equal 1, and so we take the 1 and we subtract 4/6, and we get 2/6 equals 1/3. So that the sum is still 1. Similarly, if we were to graph this, then it's not quite as featureless as before. I won't be asking you to graph any of these, but just the idea of it is important. 1, 2, 3, 4, 5, and 6. And so we've got these guys are all at 1/6, and then 2/6 is up here, and we've still got probability on the y-axis, still got the roll on the x-axis, and that leaves our 6 to have twice as high, and you can see that this isn't a uniform distribution anymore. And I said it verbally earlier, but now we'll write it down, that a probability distribution for a discrete random variable is a formula, table, or graph that gives the possible outcomes of x. So that's our variable, and here it would be our roll, for example, and their associated probabilities P of x. It's important to note that the sum of the probabilities must equal 1. And if you'd like to use a little bit of notation here, you could write the sum, because the uppercase sigma means sum of P of x is equal to 1. And one last little example to wrap things up. Complete the following probability distribution. Suppose I give you a little table that has x and P of x, where x can only have 3 values, 0, 1, or 2, and the probability of 0 is 1, and the probability of 2, is 1/10, the probability of 2 is 3/10, and what I'm asking you to do here is fill in the missing value. And since the sum is equal to 1, then this missing value has got to be 1 minus 1/10 minus 3/10, which is equal to 6/10, or 3/5. Like so.